Going to start a little mini circle unit by finishing up a few topics that we did not get to before break. This first lesson involves some proportions among chords, secants, tangents. And this is going to be in two parts. First part in this video is going to be some explanations about the formulas and where they come from. And then in the second part, I will go through some more specific examples. So here's our first property. I have two intersecting chords. E is not the center of the circle. Maybe it is, maybe it isn't. But usually it is not. And one of your last lessons that you had was looking at arcs and angles involving a setup like this. You know that this angle is the average of this arc and this arc. Well, this particular lesson doesn't look at arcs and angles. It's looking at proportions of these lengths. So we have four individual segments that are created when these two chords intersect. Start dissecting this a little bit. Going to connect these points. Going to connect CA and DB. By doing so, I've created two triangles. We know that these two angles are the same. We also know that angle C, being an inscribed angle, is 1/2 of this arc. Angle C is 1/2 of arc AD. Angle B is also inscribed. It's also 1/2 of arc AD, which means those two angles are the same. Now we have two similar triangles. Triangle CAE is similar to triangle BDE. Similar by angle. If I look at these two triangles a little more closely, I can write some various ratios. But there's a couple that I'm particularly interested in. I want ratios that use these four segments. So I want a ratio that uses CE. Well, CE is the first and third letter of this triangle. And we know that it has to match up with BE. Because the triangles are similar, that ratio is equal to another ratio we can make from these sides. I haven't used AE yet. I want to use AE. And I know that forms a ratio with DE. And if you see CE, BE is here, there's AE, there's DE. All four of our segments are in our proportion. I'm going to take this one step further. Normally we call this good, but for the purposes of this property, it makes a little more sense if we eliminate the fractions. So multiplying through by the common denominator, otherwise known as cross multiplication, will give us this. That product equal to this product. CE times DE, BE times AE. Look a little more closely. CE times DE. CE, DE. This chord was cut into two pieces. Here are those two pieces. Chord AB was also cut into two pieces. And those two pieces are both on the right-hand side. The product of these pieces is equal to the product of those pieces. And you've heard me mention many, many times, don't just memorize letters. Don't sit down and memorize CE times DE equals BE times AE 50 times. Don't repeat that over and over to yourself, because if the letters change, you're out of luck. Focus on what these stand for. These are chord pieces. The product of one chord's pieces is equal to the product of the other chord's pieces. That is our first property on proportions in circles. On to the next property. Now we're going to get outside the circle a little bit and look at two secants. Here I have a secant that starts at E, goes here. Now we know secants typically go further, but we're ignoring that. We don't want the rest of this. It's irrelevant. We only want from here to where it leaves the circle. Nothing beyond. We don't want anything beyond that. We have another secant that starts at the same point, enters the circle at A, exits the circle at B, and again, we don't care about the rest of it. We only want from here to here. So to start figuring out this property, I'm going to connect a couple of points. I'm going to connect A and D. And I'm also going to connect B and C. And besides making the picture a little more complicated, what I've done is create some triangles. And I'm going to sketch those triangles out to the side here. I want this triangle, and I want to focus on this triangle. Those are the two triangles I want to take a look at. They both have angle E. That's important. That gives us 1/2 of our angle property. Now, the reason I chose these two triangles and these two green segments was to get a common arc for two angles. Angle B on the circle, inscribed, creates this arc. Angle D on the circle, inscribed, creates this arc. Since both angles are the same type and they both make the same arc, they both are the same measure. That gives us two similar triangles, which will allow us to create a proportion. Triangle EBC, similar. Triangle EDA, that's using angle. Now, taking a look at my choices here for which things I want to make ratios out of, I've got a secant is basically gives me three options. I have the outside part of the secant, I have the inside part, and I have the whole measurement. Well, the outside part is in this triangle. This outside part is in the other triangle. That's a good start. I can make a ratio out of that. So I'm going to find EC, and it goes with EA. Now look at the inside part. This part of the secant that's inside the circle, CD. No, I do not have CD anywhere in my triangles. Nor do I have AB anywhere in my triangles. So that's out. I do have the whole secant, though, ED. That's in this triangle. And I have this whole measurement, EB, that's in this triangle. So I can make a ratio out of those. And again, I'm going to multiply this through to eliminate my fractions. And what I'm going to end up with is this equation, that's a B, where I have EC times ED, EC outside times the whole thing ED, EA times EB, EA outside times whole thing EB. And again, that's how I think you should remember this. Outside times whole. The outside part of a secant multiplied by its entire length will equal another outside part of a secant times its entire length. That is our second property of, I guess you could say, proportions involving circles. There's one more to take a look at. Point C, if point C comes this way, and point D comes that way, they're eventually going to meet. Let's say they happen to meet in a spot. That gives us this. Gives us a tangent. How do we deal with this? Well, in a similar way that we dealt with the last couple. We'll create some similar triangles and write out a proportion. This one's pretty straightforward because I don't have many choices. I'm going to connect, let me pick a different color. I'm going to connect these two and these two. And what that will do is give me a couple of triangles. I want this triangle, A, E, C, and I want this triangle, B, E, C. Well, angle E, again, is common to both. Now, here I have to be a little careful. This angle A, well, first of all, let me be careful with these angle C's. This angle C is not the same as this angle C. Angle C in this triangle is smaller than angle C in the other triangle, so they're not the same. Also, this angle A is not inscribed. For this angle A to be inscribed, one of these sides has to be a tangent. Neither one is. So angle A is not inscribed. This angle C is. This angle C is inscribed. This part of it is a tangent. So this angle C creates this arc. This angle B creates the same arc. These are the two angles that are going to be the same. Now we have two similar triangles. Triangle EAC, triangle ECB, by angle one more time. Now I've noticed something a little weird. I've got EC in this triangle, and I've got EC in that triangle in different places. This EC stands for something different than this EC. Similar to when we looked at geometric means earlier in the year. That's about to come up. So, I'm going to make my ratios similar to what I did last time. I have an outside part, EA. I have technically an outside part, EC. So I can make a ratio out of those. Now I know my inside parts are not part of these triangles, so I look at the whole thing. EB is the whole thing. EC is also the whole thing. So I get EC over EB. And when I multiply through, I get this. EA times EB. And now notice I'm going to get EC squared. It's squared because with a tangent, the outside and the whole thing are the same. Tangent never goes into a circle. It touches the point on the boundary and that's it. It never actually enters the circle. It gets right up into the doorway, but it never goes inside the door. So, to put this into words, it's the same as before, outside times whole, but notice with the tangent, the outside is the whole. On one side, we have two separate measurements. On the other side, we have the same measurement twice. That is our third and final property. So, we have two intersecting chords. Multiply the pieces together. Two secants that start from the same outside point. Outside portion times the whole thing for each one are going to be equal. Secant and a tangent, we still have outside times whole, and then on the other side we have the tangent squared because the outside is the whole. If you want some more examples, some more specific examples with some values, the next video will have those.